All right, welcome back everyone to this explainer. Today, we're going to tackle what is arguably one of the most notoriously intimidating topics in advanced electrical drives, and that is the dynamic analysis of induction machines. Look, I know, you hear matrix math, time-varying inductances, complex coordinate systems, and you just want to groan, right? But stick with me. Today, we are taking a heavily physical, super visual approach to completely demystify these complex AC machines. By the end of this, you are literally going to see the absolute elegance behind all that math.
Okay, so here's our game plan for today. We'll start with the challenges of the three-phase system, move into the main purpose of the DQ transformation, then look at the Clark and Park geometry. After that, we'll see exactly how the DQ axis works, how it's used in industrial drives, and finally, we'll wrap up by building a DQ model on MATLAB.
All right, let's jump right into part one, the challenges of the three-phase system, or what I like to call the ABC complexity.
So to really appreciate the brilliant engineering solution we use today, we kind of have to understand the mathematical nightmare of traditional three-phase analysis first. Just look at the sheer contrast on screen. On the left side, we have our physical reality, right? The ABC reference frame. In an induction machine, your stator and rotor flux linkages depend entirely on the rotor angle. Why? Well, because the mutual inductances between the windings are position dependent. They're constantly changing as the rotor spins. So you're dealing with time-varying sine waves and highly nonlinear equations. Honestly, it's a stability nightmare. But look over at the right side, the DQ simplicity. Transforming to the DQ frame gives us these beautifully stable, constant, DC-like signals with completely decoupled variables. It is basically the absolute perfect environment for applying your standard PI control.
Which brings us to section 2, the main purpose of the DQ transformation, basically chasing the DC machine. So you might be wondering, why on earth do we endure all these mathematical gymnastics in the first place? Well, what are we actually chasing here? This graphic brilliantly illustrates our ultimate goal. I don't want you just memorizing matrices. I really want you to visualize this. Using the DQ transformation lets us imagine a totally hypothetical machine with two orthogonal equivalent windings. You've got the D-axis for magnetic flux and the Q-axis for torque. Essentially, we are taking this rugged, highly complex three-phase AC motor and mathematically forcing it to mimic a separately excited DC motor. That physical insight right there, that establishes the absolute foundation for dynamic analysis because it finally gives us independent control of flux and torque.
Moving right along to section 3, Clark and Park geometry, and rotating the reference frame.
Okay, let's get into the math and see how this actually builds. Now, moving away from just rote memorization of matrices, the absolutely crucial thing to grasp is the geometric logic of the Park and Clark transformations. These are two very specific physical moves. Step 1 is the Clark transformation. Think of this as literally flattening our three-phase ABC vectors right onto a two-dimensional stationary plane. We call that the alpha-beta plane. But we don't stop there. Step 2 is the Park transformation. Here, we take that flattened alpha-beta frame and we rotate it by an angle theta to align it with a rotating reference. We are quite literally spinning our coordinate plane to catch up with the machine's rotating magnetic field. How cool is that?
Now, for section 4, how does the DQ axis actually work? Let's look at the physical reality.
I want you to just pause for a second and really think about what these mathematically rotated axes represent in the physical stator. What's super interesting here is the visual transition. Look at the left side. We're taking three physical windings spaced 120 electrical degrees apart, and we replace them with what you see on the right, two hypothetical orthogonal windings spaced exactly 90 degrees apart. And because those direct and quadrature axes are exactly 90 degrees apart, guess what? Their mutual magnetic coupling is 0. Boom! We have completely eliminated the mutual magnetic coupling that makes AC machines such a headache to control, and we've turned complex AC signals into pure DC clarity. And as you'll see, this geometry directly translates right into our equivalent circuits. By choosing our rotation speed carefully in our reference frame, like, say, setting it to the synchronous speed, we literally freeze those oscillating AC signals into steady DC values. Take a close look at the speed-voltage terms in these equations, those omega terms. By doing this, we've created two completely separate circuits, the D-axis and the Q-axis, and they are coupled only by the magnetizing flux. This gives us the perfect linear plant for our PI controllers to act on.
All right, section 5, DQ use in industrial drives, focusing on vector control.
So let's take this geometric theory and apply it to the real world of modern industrial motor drives just to see why this matters so much. What you see defined on screen is the absolute holy grail of AC motor control, field-oriented control, or vector control. Because we successfully transformed our messy three-phase system into a clean, two-axis orthogonal system, we can now dictate the magnetic flux strictly using the d-axis current. And we can independently command the electromagnetic torque with the q-axis current. I mean, without the DQ transformation, modern variable speed drives simply would not exist in the way we know them today. It's a total game changer.
And to actually build these advanced control systems, we rely heavily on simulation models. Here's a general simulation block diagram for an induction machine. I want to draw your attention over to the reference frame selector on the left side there. Depending on what exactly we want to analyze, say we're looking at stator transients versus rotor dynamics, we can use this selector to seamlessly shift our mathematical perspective. We can bounce between the stationary frame, the rotor frame, or the synchronous frame, all just by changing our arbitrary speed omega_a.
And finally, Section 6, the DQ model on MATLAB and building the actual simulation.
Okay, let's move from industrial theory over to your final project for this course, building this exact dynamic model in MATLAB and Simulink. Think of this as MATLAB 101 for induction machines. Notice how all that complex matrix math we just learned is so cleanly boxed into continuous Simulink blocks. We immediately transform the three-phase grid voltages into our workable DQ frame using these ABC to alpha beta and alpha beta to DQ blocks, right before hitting that massive state space equation block in the center. This modular design makes solving those highly coupled differential equations incredibly clean and efficient.
Now, to simulate this successfully, you're going to want to follow these specific steps. First, implement those transformation blocks. Second, build out your reference frame selector so you can actually choose your rotation speed. Third, you need to accurately program the state space model derivatives for your current and flux. Fourth, use those states to calculate the electromagnetic torque. And fifth, implement the equation of motion to get your rotor speed, making sure to feed that back into the system. If you map these dynamic equations accurately, your virtual machine will spin for sure.
Before we wrap up, I want to leave you with a bit of a provocative thought to ponder before our next lecture. If our entire DQ transformation relies on a beautifully balanced, symmetrical three-phase system to cancel out to zero, how would you adapt this exact simulation model if the motor experienced an asymmetrical grid fault? Think about it. While the DQ frame perfectly simplifies balanced systems, the real world is often unbalanced and honestly pretty messy. Ponder how the math would break down in that scenario because we are going to pick up exactly right there next time. Thank you so much for joining this explainer and keep exploring.
Welcome back to the Explainer, everyone. Today we are taking on a genuinely fascinating challenge for our Advanced Drives course. We're going to completely demystify exactly how we control alternating current machines under dynamic conditions. If you've ever been in a modern electric vehicle and wondered how it gets that instant, perfectly seamless acceleration, well, you're about to find out how the sausage is made.
So let's kick things off with a massive question, one that honestly had engineers scratching their heads for decades. How do we take a highly complex, heavily coupled AC machine and control it with the exact same snappy, precise response as a simple DC motor, especially when speeds and loads are just constantly dynamically changing? This is the high-stakes engineering problem we are solving today. To unlock this, we are going to lean heavily on the pedagogical approach of Ned Mohan. His philosophy is absolutely spot on. We need to build a physical picture in our minds before we immediately resort to drowning in mathematical transformations. If we can firmly grasp the physical reality of what's actually happening inside the air gap first, I promise you, the complex math will follow naturally and make perfect sense. All right, here's our roadmap for today's explainer. First, the dynamic control problem. Second, a physical transformation approach. Third, stator and rotor DQ windings. Fourth, the mathematics of DQ. And finally, mastering torque and flux.
Let's jump right into Section 1. The dynamic control problem.
Okay, so take a look at the traditional ABC phase setup right here. The
The fundamental flaw in using this for dynamic control is staring us right in the face. The phase quantities, specifically the flux linkages and mutual inductances, they heavily depend on the rotor angle theta m. Because the rotor is constantly spinning, these variables are constantly changing. Trying to write a control algorithm for position-dependent, highly coupled variables is, well, it's a nightmare. It's incredibly complex.
So the big takeaway here is the stark contrast between these two paradigms. We desperately must escape the messy reality of position-dependent ABC phases, where a change in one phase just completely interferes with the others. Instead, we are migrating to DQ quantities. By the end of this explainer, you'll see exactly how these orthogonal DQ axes give a simplified and, most importantly, totally independent control.
Moving right along to Section 2, a physical transformation approach. Now, I know most of you have encountered Park's transformation in earlier circuits classes. You probably remember it as this dry, purely mathematical matrix operation. But I want you to completely shift your perspective today. Fundamentally, Park's transformation represents the physical realization of two hypothetical, visually distinct orthogonal windings that perfectly replace our three physical ABC windings.
And this graphic right here brilliantly illustrates exactly what we're aiming for. The exact same air gap magnemotive force, the MMF, that's produced by three overlapping phase windings can be identically created by just two orthogonal windings. One is positioned along the D-axis and the other along the Q-axis. We are essentially tricking the motor's physics. From the perspective of the air gap, these two virtual coils are literally indistinguishable from the three real ones.
Let's look at Section 3, Stator and Rotor DQ windings. Here's where it gets really elegant. By placing our virtual windings along the D and Q axes, we've forced them to be at a perfect 90-degree angle to one another, right? So the absolutely crucial point is that this exact orthogonal orientation guarantees zero magnetic coupling between them. A change in the D-axis current produces flux that has absolutely no effect on the Q-axis winding, and vice versa. We have successfully uncoupled the machine's magnetic fields.
Furthermore, by intentionally aligning our virtual stator and rotor DQ windings on the very same axes, something incredible happens. Because of this clever alignment, the mutual inductance between the stator's D-axis winding and the rotor's D-axis winding is exactly the magnetizing inductance, Lm. This beautifully and directly links our primary fluxes without any of that position-dependent crosstalk ruining our calculations. It's a real game changer.
Which brings us to Section 4, the mathematics of DQ. Now, to derive the actual currents needed for our virtual windings without getting lost in a sea of algebra, we follow a very strict logical progression. Step 1, we mathematically equate the MMF of the three-phase windings to our two DQ windings. Step 2, we apply a 2/3 turns ratio. We have to do this to maintain equivalent MMF amplitude when condensing three phases down into two. In step 3, we extract the geometric projection vectors along the D and Q axes.
When we actually execute those steps, we derive the specific transformation matrix. Notice how that 2/3 ratio naturally falls out right in front, giving us the exact cosine and sine geometric projection vectors we just visualized physically. Guys, this isn't abstract math. It is a direct, literal translation of the physical coil geometry we just established in the air gap.
Seeing how this builds into an actual control system is just so cool. Physical phase currents A, B, and C are continuously processed through our transformation matrix, and it spits out our new orthogonal ISD and ISQ control currents. This specific block diagram, this architecture, is the actual software running on the microprocessors inside modern electric drives today.
Finally, let's wrap up with Section 5, Mastering Torque and Flux.
Just look at how incredibly clean this net electromagnetic torque equation becomes under the DQ framework. Tm is simply proportional to the magnetizing inductance Lm multiplied by the difference of the cross products of our DQ currents. It is completely 100% free of those messy position-dependent theta variables we wrestled with in the phase analysis. So, let's summarize the sheer engineering brilliance of analyzing machines using DQ windings. First, we achieve zero magnetic coupling between our control axes. Second, this yields radically simpler mathematical expressions that our microcontrollers can actually process in real time. And third, the ultimate prize, we gain completely independent control of the air gap flux, which is handled by the D-axis, and the electromagnetic torque handled by the Q-axis. We've literally turned a complex AC motor into a highly controllable DC motor equivalent.
So I'll leave you all with a thought to chew on before your next drives lab. If we can truly control torque and flux completely independently, how will you apply this exact theoretical principle to innovate the power processing units for the next generation of hybrid electric vehicles? The future of clean transportation absolutely relies on the very math and physics we covered today. Thanks for joining me for this explainer, and I'll catch you in the next one.